actual biome, because I know for experience that is an interesting trip to actually get there.
Yeah. We are organizing the next trip. It's a typical French conference. We are organizing it in Isola d'Elba, and you can reach Isola d'Elba only by boat. You cannot go there by plane. So wow, it's a bit a trip.
You know, I think it's a way to make a selection. You know, only if you're a good swimmer, you can get to the meeting.
Exactly.
Good morning, Greta.
Hey, Greta.
Greta.
Well, at least it is morning in sort of our part of the world, Smella. So.
Yeah.
Good morning.
I was counting on you being on that side of the ocean.
Right. Yes.
By the way, Greta, you're coming to Zurich, aren't you, at some point?
Yes, I will. Yes. Yeah, that is sometimes in September, I think. So.
Yeah, I forget. I spoke with Annalisa about it, but I forget.
Okay.
Because I think it was, of course, it was moved because of the pandemic, so I lost track of the calendar.
Right.
Okay, we are on YouTube, and I'm going to open the room in a minute, if you don't mind.
Yes.
And then, Alfredo, you chair.
Yes,
right?
I will just introduce you briefly, Filippo, and then I leave the floor to you.
Thank you very much.
45 minutes, okay?
Of course.
So it's 3 p.m. here where I am, and I think we should start. So I welcome everybody. I ask everybody to please shut off your video and mute yourself. And I'm ready to introduce the speaker of today of the International Journal of Multi-Phase Flow Spotlight Seminar. The speaker of today is Filippo Coletti, and I'm not sure if I see Filippo still. I lost control. Filippo, you're here. Just Filippo. I think I don't see Filippo.
He was here.
He was here just a second ago, and in fact, I had the suspicion that we just lost him. Hope he can get back immediately.
Okay, I just in a few. Let me send him an email. Finding out.
So in the meantime, I just thank everybody for joining us. I know it's hard because our seminars range all over the world. And so there is, I think, about 16 hours span from the people in the West Coast of the US and the people in Japan who are kindly attending the seminar. So I really thank everybody for the effort, for the special effort they're making to attend this seminar. I hope that the speaker, I hope that the speaker today will join us in a few seconds. And we are pretty sure
Yeah, I sent him an email. He was here just a few seconds ago, and we were all talking.
Yeah. There was this usual, just to inform everybody else.
Yes, he's back.
Filippo,
He's
you
back
are here again.
He's back
we were
here.
worried.
Hi, sorry, my Zoom played a game on me just at the right time. Hi, everybody.
No problem, Filippo. So I just started introducing the seminar series, and Filippo Coletti will be the speaker of today. Just very briefly, we know many of the papers of Filippo, but just very briefly, Filippo graduated in Perugia in mechanical engineering in Italy, and then he got his PhD doing his work in von Karman and getting his title at the University of Stuttgart. And then he was postdoc in Stanford and assistant professor in University of Minnesota. And then just during the pandemic, just 2 years ago, he joined ETH Zurich, where he's now associate professor of experimental fluid mechanics. So today he will tell us about particles and snowflakes which are falling through turbulence. And thank you very much, Filippo, for being with us.
Thank you, Alfredo, for the introduction, and to the IJMF family for the invitation. Thanks everybody for attending. It's really a pleasure to give this talk to this great audience today. So today I'll tell you a story about particles in turbulence, which are a passion of mine, and I find them so important for so many things. Of course, process engineering, but also in energy harvesting devices. They can in fact be beneficial or detrimental. And even if we have a large object, say a plastic bottle, this can actually degrade and break down into small particles and then pollute irreversibly our waters. But then a lot of inspiration comes also from particles in turbulence in the sky that offer countless examples of important applications. And finally, the pandemic really showed us all how small particles in a turbulent airflow can rule our lives. And in our group, we study particle-laden flows and particle-laden turbulence flows more often with a variety of techniques and spanning a very broad range of concentration and applications. And today I'll actually focus on the left-hand side of this slide, which is the most dilute volume fraction in a seemingly simple configuration. In fact, this configuration is so simple that I could put it down in a pretty elementary, seemingly elementary question in a fluid mechanics 101 type of exam. So say that I have a dilute suspension of spherical particles falling in a turbulent fluid flow. And say that I know, in fact, the particle properties very well. I know their size and their density. And so also imagine that I know everything about the turbulent flow. And to make things even easier, say that the particles are so small and so sparse that they have a negligible effect on the turbulence. Now, under those conditions, I have only one question today. What is the fall speed of the particle? And so this problem actually has impacted my own personal life in ways that I was not anticipating when I was growing up as a kid in Italy. Because what you're seeing now is the polar vortex hitting North America, and specifically Minneapolis, Minnesota, where there was my home for about 6 years. And when that happens, abundant snow falls on you. And this is a photo from the inside of my house, where you can see my balcony being blocked by about a meter of snow, locking me in with my children. And if you've ever been locked down with children, you know that things can go south pretty quickly. But besides my, let's say, personal struggle, the very fundamental question that we can ask is simply, what is the fall speed of snow? And that sounds like a very basic question, but it was shocking to me to realize that current models that are meant to predict the fall speed of snow are based, even today, on a single study from 1974 that observed in the field exactly 376 snowflakes. And that's a problem. That's a problem because we can't afford not to know the fall speed of snow, because the fall speed of ice particles and snow particles in atmospheric clouds actually turns out to be one of the factors that impacts the most the sensitivity of climate projection models. So back to our fundamental problem of particle in turbulence, let's consider what the scales in terms of spatial and temporal scales are. So if I have a particle of diameter dp, let's say, I'm going to say that this particle has also an aerodynamic response time tau p. And this particle is immersed in a turbulent flow. And of course, there I have a range of scales from the dissipative Kolmogorov scales, which are demarked with eta, to the integral scales, which are demarked with capital L. So if I assume that the particle is small, even smaller than the Kolmogorov scales, then the crucial non-dimensional number is really the Stokes number. So the ratio of the response time of the particle to the characteristic time scale of the flow. And of course, I can define Stokes based on the Kolmogorov scale or the integral scale. I guess the most common definition is the one based on the Kolmogorov scale. And it is well known for a long time that for particle with the Stokes number based on Kolmogorov of order 1, then I have interesting phenomena happening. Specifically, the particles tend to visit preferentially regions of high strain and low vorticity. And so they tend to cluster also in specific regions of the flow. But of course, by doing all of this, I'm neglecting gravity. When there is gravity, the particle will have a characteristic fall speed that in a quiescent fluid would be tau p g. And that scale I can compare with the velocity scale of the turbulence, which again will span the full range of scales from the dissipative to the integral scale. In this case, the integral velocity scale will be the RMS velocity fluctuation. So then I can also define a non-dimensional number, typically called the settling velocity, SV number, where I take the ratio of this still fluid settling velocity over either the dissipative or the integral scale of the velocity fluctuations. So with all of that, the fundamental question really is, how does turbulence affect the fall speed of particles? But in fact, there are arguments for the turbulence to increase or decrease the fall speed of particles. For example, turbulence can increase the fall speed of particle if, for example, as postulated by Wang and Maxi, have so-called preferential sweeping, which means that particles favor downward regions of the turbulent eddies, and so they fast track their way downward in a turbulent flow. Or I could have a mechanism that reduce the fall speed due to turbulence. And I could have, for example, a relatively small inertia particle trapped in vortices, or the ones with a higher inertia could bullet vertically through the turbulent, but then would spend more time fighting the upward gusts of the flow rather than going down the downward gusts, and that would be called loitering. And then because the drag is typically nonlinear for particles above a certain level of inertia, then the nonlinearity of the drag will also penalize those moments in the upward gusts, so they will also slow down overall the fall speed. But of course, if you want to have a clear quantitative understanding, we need to consider all the details of the particle and turbulence interaction. And then, of course, we might want to simulate the whole process. The standard quote approach in the last several decades has been the point particle approach. So you basically use the Maxi-Rayleigh-Gatignol framework, and you write a particle equation of motion, taking the particle as a material point. That's a very powerful approach. However, it does assume that the particle Reynolds number is small, and the particle shouldn't affect the flow. And if it does affect the flow, then, for example, to calculate the correct form of this drag, you should know the undisturbed fluid flow velocity, which is not necessarily trivial to determine. Of course, that can lead to, of course, interesting predictions, but sometimes also hard to quantify, to compare with experiments. For example, this is an example from a beautiful paper from Good et al., in which they measured and simulated the fall speed of particles in turbulence. And as you can see, for a wide range of the settling velocity parameter, the gap between the experiments and the simulations is substantial. The other end of the spectrum is particle result simulations, in which you don't need to model the forces because you're resolving the interfacial interaction between the particle and the fluid. But of course, this is very computationally expensive. And so you are limited in terms of the number of particles and the Reynolds number of the particle themselves, but also of the turbulent flow that you can simulate. So for me, being experimentalist, you can guess that my approach is rather to make no assumptions of the governing equations and then do laboratory experiments and let nature follow its due course. To find most fundamental results, we try to minimize confounding factors by looking at rigorously size-selected particles, all spherical, and we study them in canonical turbulent flows. Today, I'll talk a lot about homogeneous turbulence. And then we try to measure everything, or at least the most that we can. the turbulent flow field, of course, covering all scales from integral to Kolmogorov, and also the particle position in time so that we can get velocity and acceleration information. And the goal is to get a really mechanistic understanding of this complex interaction so that we can define what the minimal physics is that we need to retain for such understanding. How we do this? Well, conceptually, we can create homogeneous turbulence. Conceptually, it's easy in PowerPoint. Let's see if we can also do it in real life. In PowerPoint, you just have a large box, and then you fire jets from at least two sides, and you pulse these air jets in a way that you create a region of intense turbulence at the center, where there is no or negligible mean flow and negligible shear. And then you drop particles in such a region of homogeneous turbulence, and then you shine a light sheet, and you use a high-speed camera to image your multi-phase flow. In reality, you do a complicated CAD design, and then you go to the shop and you build it. But that's what we did in Minnesota. We built this large chamber, which has now been updated and rebuilt here in Zurich, with the 256 air jets, which are individually computer controlled, and the full optical access for us to have a good view of the dynamics. And this is a snapshot, a couple of snapshot of the facility with a close up on the jet array. And then we do high speed and low speed, high resolution imaging for both particle image velocimetry and particle tracking velocimetry, as I will tell in a minute. And it's nice to have a facility in which you can actually go inside, take pictures with your favorite students, or at least the one student that makes you look tall in the picture. This is Lucy Baker, who produces some of the results that I'll present today. And then, of course, we drop in this facility our particles. We use typically glass spheres, again, size selected, but sometimes you also use a lycopodium, which is a spore that is naturally size selected. So lycopodium figured out in its evolutionary path that 30 micron was the right size for it to reproduce best, and so is very narrowly distributed around that size. And we drop these particles into the chamber through a long chute, so they reach terminal velocity before entering the homogeneous turbulent region. And we cover a range of Stokes number and settling velocity parameter kind of centered around order unity. And then we also span a fairly large range of volume fractions, from the fully dilute, in which we don't expect any two-way coupling with the turbulence, all the way down to a regime in which we do expect, and we do find, in fact, a significant back reaction of the particle on the turbulence. And then we do our multi-phase imaging, which means that we take videos like this, in which you can make out both bigger and brighter particles, and those are the inertial particles, for example, let's say a 50 micron glass bead, but also smaller and dimmer tracers. So those are typically 1 or 2 micron olive oil droplets, which follow the flow perfectly, and they don't have any measurable settling velocity. And then we separate our data in particles only and tracers only. And we perform particle tracking velocimetry on the first data set type of images, and particle image velocimetry on the latter, so that we get our Lagrangian particle information and our Eulerian fluid information with a significant temporal and spatial resolution, such that in a few seconds of measurements, we're already gathering hundreds of gigabytes or even terabytes of data. So to process all of this, we need to resort to computer clusters, in fact. And so just to give you an idea of the characteristic of the turbulence that we can generate in this facility, we can reach a Reynolds number based on the Taylor microscale that exceeds 500 with integral length scales of order of 10 centimeters and a sub-millimeter Kolmogorov scale. The RMS velocity fluctuation, as you can see, is about an order of magnitude larger than the mean flow velocity. So that's really what we want to investigate the motion of the particles without bias, a flow with virtually zero mean flow. And then the important part here is that the turbulence is homogeneous over scales much larger than the integral scale of the turbulence, so that the turbulence can really develop in its natural cascade without significant effect of the boundaries. And this is just a snapshot of instantaneous entropy that shows really the range of scales of the intense vorticity vertical motions. But again, our focus is really on the particles. So we investigate the spatial distribution of the particles using multiple methods, including Voronoi tessellation. which was introduced in the early 2000s, and we used extensively since then. Essentially, what is done, if you don't know the technique, it's pretty simple. You tessellate the domain in a way that every particle is inscribed in a polygon with the specific features. Features is that every point inside the polygon is closer to the particle that contains than to any other particle. And essentially, you have regions in which particles are very close to each other, so the polygons will be very small. Like if you were living in a crowded part of downtown, you'll have a small apartment. And then there are regions in which particles are very dilute, so they are far away from each other, so they're inscribed in relatively large polygons, as if you're living, let's say, in the suburbs. And then we can identify contiguous regions in which particles are very concentrated, which means that you have contiguous polygons below a certain threshold, and those are what we identify as clusters. Now, these clusters can be very small and very large. For quite some time, clusters in turbulence have been thought to be almost exclusively driven by small-scale Kolmogorov scale vortices, because those are the ones that spin the fastest, and so they would centrifuge most efficiently the particles out of their core, and so they would lead to clusters of order of a few Kolmogorov length scales. But in fact, what we see is that the clusters follow a power law distribution, which by definition covers very many decades. And in fact, in the snapshot you see on the left, you can see a cluster of particles about 30 centimeters, so pretty much of the size of my head, falling all together through turbulence. Now, these particles are not touching each other. They're still relatively far from each other, but they are much denser in their concentration in the cluster compared to outside. But now the real question, of course, is how fast do the particle fall in this turbulent flow environment? And so here I'm going to present the results in this kind of Carper plot, in which I have two axes for the two main parameters, non-dimensional parameters that we define. On the abscissa, you have the Stokes number, so basically how inertial the particles are. And in the ordinate, you have the SV number, so how fast the particles are drifting downward by gravity compared to the velocity scale of the turbulence. And then what you see is that for particles which are relatively massive, so they have a Stokes number much larger than 1, and an SV number also much larger than 1, the settling velocity is of the same order, very close to the settling velocity that you would have if you were falling in the quiescent fluid. So W0 is just tau pg, so it's the settling velocity that you expect for this particle without any turbulence, whereas Ws is the one that you measure. So this ratio being close to 1 means that turbulence is not really affecting the fall speed significantly. But then, as you can see, for Stokes number and SV numbers of order 1, so for particles which are inertial but not at all ballistic, then you do have a substantial, I would say a dramatic increase in the fall speed. In fact, a multifold increase of the fall speed. We find a 2.5 and even slightly larger enhancement of settling velocity because of turbulence. And the reason why this is happening, we believe, is preferential sweeping. And in fact, this has been believed for quite some time, but we have really, I would say, demonstrated that that's the case. Preferential sweeping, as I already mentioned, is a mechanism by which the particles would favor the downward side of the eddies. And these will be particles that, in fact, are supposed to also be centrifuged out of the eddies. So we do expect it for particles with Stokes number of order 1. And when they do that, then they follow the path of minimum resistance, and so they fall the fastest. And of course, they also visit regions of the flow which are pointing down. To demonstrate that that's the case, here I'm plotting the fluid velocity in the vertical fluid velocity, WF, interpolated at the particle location, XP, ensemble average over our measurements, and then normalized in this case by the RMS velocity fluctuation of the flow. And then plotting is against the Stokes number, showing that this is negative for all types of particles. So there is always a tendency of the particle to visit regions of the flow which are pointing down. But this tendency is so much more intense for Stokes number of order 1, which is consonant with what I already showed in terms of our results. So in terms of this increase of settling velocity for Stokes number of order 1. What is also interesting is that the particle cluster, in fact, fall even faster than the average particles. Now remember, already the average particles can fall 2 or 2.5 times faster than particles that would fall in a quiescent fluid. But if you isolate the clusters, and that's the subscript C there, then you see that the BC over BS ratio tend to exceed 1 by a lot for the large clusters. So if AC is just the area of the cluster, which, as I showed, is distributed in a power law form. And then the largest one, of course, much, much larger than the Kolmogorov scale. And so, as you can see, the largest clusters can fall 4, 5, 6 times faster than the average particle. So this is really a massive increase of the fall speed of clustered inertial particles in turbulence. Now, the question that I also want to ask, although it's kind of a side question compared to the fall speed question I asked at the beginning, is whether particles also modify the turbulence. And I guess I can already tell that they do, simply because this is in fact a very well-known fact in particulate and turbulence. When you have even a minute concentration, just a bit larger than a part per million in volume fraction, you already expect significant change in, say, the turbulent kinetic energy. But do they inhibit turbulence, or do they enhance, augment turbulence? In fact, just like for the fall speed, we can put forward arguments for both of these answers. Particle can inhibit turbulence, for example, because they actually increase the effective density of your mixture. They can increase the effective viscosity of the mixture, and definitely they would increase the dissipation, because they produce this. They cause a significant dissipation just at the interface between the solid particles and the fluid. But there are also reasons to expect that a particle would augment turbulence, because these particles can release kinetic energy when onto the fluid. Above a certain particle Reynolds number, they can shed the wakes that can be relatively energetic into the fluid. And they can even cause instability in a kind of a dusty gas sense, because there will be significant density gradients in the gas particle mixture. But the bottom line is that we don't know. The bottom line, at least to this day, is really that it was in 2010 in this review from Bala and John Eaton, that this field is very much open for fundamental investigation, because there isn't no close answer to the question here. So if I look at the literature, in fact, and I look at classic studies, for example, from John Eaton, with whom I worked during my postdoc for several years at Stanford, classic result is that the turbulent kinetic energy is in fact reduced massively by the presence of particles, compared to the turbulent kinetic energy that you have in an unladen system. As you can see here, as the particle mass fraction is increased up to, in this case, 40%, you have a drop of about 85 or 90% in the TK, so a massive drop. However, consider this is data from my old boss. Okay, so this is data from John Eaton, Eaton's lab, with whom I worked successively for several years, a number of years ago. Then, when we consider our measurements in our homogeneous turbulence chamber, we found exactly the opposite. We found that, in fact, when we increase our mass fraction of particles up to about 10% of mass loading, we saw more than a doubling, again, almost a tripling of the turbulent kinetic energy compared to the same fluid, the same forcing without any particles. And that's an awkward situation when you have to go talk with your old boss that is going to be your kind of your mentor forever, and you have to tell him that you're finding exactly the opposite result. But fortunately for me, this has nothing to do with his measurements being wrong, or I hope not my measurements being wrong, but there's rather a lot to do with the difference in the Stokes number of the particles. At least this is what I believe. The Stokes number of the particulate and turbulence experiment in John Eaton's lab mostly were relatively massive, so Stokes number of order 50, so particles that do not cluster, and in fact, they behave more or less ballistically with respect to the turbulence. Whereas we have been focusing specifically for this data I'm showing you now on Stokes number of order 1. And so this is, I believe, what the cause. And in fact, I think that the turbulent kinetic energy might not even be the right observable, or at least the only observable that one should refer to understand what's happening in this system. Because of course, the turbulent kinetic energy is just an ensemble result of the spectrum of energy, or in this case, what I prefer to plot, which is the second order velocity structure function. In other words, how the energy is distributing through the scales of the turbulence. And what we see here is that for unladen unladen turbulence, we do retrieve the 2/3 scaling of the structure function with the separation R. But then as we increase the volume fraction, we have a pivoting of these structure function around a scale of about 40 cosmograph. So basically the particles are sucking energy at the large scales, but they are injecting a lot more energy or comparable amount of energy at the small scales. And this has been already argued by numerical simulations before, but I believe this might as well be the first time that is shown experimentally, at least for a fully turbulent particle-laden flow. And so the argument to explain the difference between the high Stokes number and the small Stokes number is that this mechanism of injecting a different amount of energy at different scales is very much dependent on whether the particle move ballistically, and so they visit with the equal probability every location of the flow, or whether they cluster as the Stokes 1 particle that we use to. So with that, we close the parentheses on the two-way coupling, and we go back to our initial fundamental question: are snowflakes just inertial particles in turbulence, right? Can we find signs in actual snowflakes that what we learned in particle-laden turbulence is relevant? So can we use our wisdom from particle-laden turbulence studies to explain or to inform knowledge in atmospheric science? So to answer this question, with colleagues of mine when I was in Minnesota at the St. Anthony Falls Laboratory, we carried out a very exciting research program over multiple years. Basically, we drove for about 40 minutes out of Minneapolis, so exactly in the middle of nowhere, if you've ever been there, in Rosemont exactly, where the University of Minnesota has a well-instrumented field site on a very flat region where you can do pretty high resolution measurements of atmospheric turbulence. And so there we carried out a field campaign where we characterized the atmospheric turbulence using multiple sonic anemometers. And at the same time, we also wanted to know whether the particles, so the snow that we were looking at, were comparable to, let's say, our particles. And specifically today, I will show you results about Graupel, so about snowflakes, which are in fact fairly round and fairly compact, unlike, for example, very dendritic crystals that you could see in Disney movies that very likely behave much differently from small spherical particles. And the characterization of the snowflake shape and size was done by digital inline holography, a portable digital inline holography system that allowed us to characterize this the size and shape of our particles, quote, very carefully. And I should remark that none of this would have happened without the contribution of my collaborators and friends, Michele Guala and Jaron Hong at the University of Minnesota. They were fantastic to work with over the years. We had a lot of fun putting together these studies. And then once we characterize our particle types and our turbulence properties, then we can do what we do best, which is to basically track particles in turbulence. And we applied pretty much the same philosophy as we would do in the laboratory, which is to shine a bright light sheet in our region of interest, and then use a high-speed camera to track things. The only difference is now we are in the middle of a big field in outdoor Minnesota at night, and so what we use is obviously not a laser sheet, because I guess you don't get to blast a laser light in the sky in the US, especially if you're not a citizen. But I guess in any case, it's kind of frowned upon. But instead, what we used is a powerful searchlight shined on the curved mirror, so it illuminates kind of a 30-centimeter thick sheet that extends tens of meters up in the sky. And then we use high-speed cameras that we orient carefully, so we can then correct for the deformation due to the inclination. And we image a very large field of views. In this case, a 7 by 4 meter field of view plays kind of 12 meters from the ground. And then what we get is this. And I don't know if it conveys well through Zoom, but this is absolutely stunning and in fact easy to work with as a video record for particle tracking velocimetry, because these particles that you see here are very bright, and they are shining on top of a very dark background. And that's simply because we are doing measurements at night, and we are shining a light over a very reflective and diffractive object, which is a snowflake. So with that, we have a relatively easy time, in fact, tracking hundreds of thousands of trajectories, from which we can gather a lot of higher order statistics. For example, we can gather acceleration, and they help us answering the question, what is the Stokes number of a snowflake? Because if you want to say something fundamental about particle-laden turbulence, or I guess about snowflakes in turbulence, using the framework of particle-laden turbulence, we cannot move away from the question of the Stokes number. So what we use is the classic framework of inertial particle in homogeneous turbulence. And what we know is that the distribution of the acceleration of particle in turbulence is very sensitive to the Stokes number itself. So if you have a tracer with a Stokes number virtually zero, this has very fat tails, which in fact become much thinner as you increase the Stokes number. And in fact, when we take our data, which is our black triangles here, in terms of a PDF of acceleration, and we plot it on top of a number of other classic studies in homogeneous turbulence with inertial particles, we see that we fall very much on top of this data for a relatively narrow range of Stokes numbers, Stokes between 0.1 and 0.4. Now, this is a relatively large range because it's a factor of 4, but it still locks pretty well at least the decade in which we are moving. So if we can assume that the particles, the snowflakes, really follow the same phenomenology of inertial particle in turbulence, then we can deduce from these measurements, their Stokes number. And their Stokes number really just tau p over tau eta. So this is the aerodynamic response time divided by the Kolmogorov timescale. And we know the Kolmogorov timescale because we have detailed, high resolved measurements of the atmospheric turbulence. And so from that, we get very simply an estimate for tau p, which is between 12 and 48 milliseconds. So that's, again, a broad range, is the usual factor 4 in there. But from that, we get a fairly well-bounded, conservative estimate of the fall speed that the snowflakes should have in quiescent air. In other words, if I take a particle of response time tau p and I drop it in quiescent air with no turbulence, there's only one velocity it can reach, tau p g. That's my W naught. If I now compare this expected tau p g W naught range to the probability distribution of the velocity, settling velocity that we measure in the field, we see that there's a striking difference. We see that there is about a factor of 3 faster falling of the snowflakes in turbulence. So again, what we deduce is that turbulence is increasing the fall speed of the particles by a multifold time, which is consistent with the idea that this Stokes number, this particle have a Stokes number close to the order 1, for which we saw from our lab experiments that we expect preferential sweeping to be very powerful and to produce such a dramatic increase in fall speed. Great. So now we learn something we hope fairly fundamental about inertial particles in turbulence, but only away from the ground. Because close to the ground, things are very different, of course. This video that I'm showing was shot with a smartphone by my old postdoc, Tim Berg, who now, in fact, is a professor in Utah. And Tim is a morning guy, so he was walking over the frozen Cedar Lake, and he took this beautiful shot about dawn. And as you can see, you can identify the famous streaks of particles. In this case, those are, of course, small ice crystals and the snowflakes picked up by the wind as it shears on the ground. And this situation is, of course, very different from a high altitude or simply a turbulence, let's say some 10 or 20 meters from the ground, where the shear is so much less, and you have, in fact, something much closer to homogeneous turbulence. So then we turn to this fundamental problem, which is a different one, and is another classic problem, the one of particles suspended in a turbulent boundary layer. And I cannot stress enough how much this is an old problem, a problem faced by Rouse and by Prandtl after him. It's a problem in which you have particles which are heavy, so they fall by gravity, but they also are adapted in full suspension by a turbulent boundary layer. So what they assume, Rouse and Prandtl assume in their theory, independently, is that there is an equilibrium between, or that you are already in an equilibrium condition. So essentially, the settling by gravity and the turbulent suspensions are in equilibrium. So the vertical flux, which is the sum of these two components, is essentially zero. And then what you also can assume is that there is a Fickian diffusion. So the most classic turbulent diffusion basically follows the Fick's law, meaning that the turbulent flux of the particles upward goes in the direction of the gradient through a diffusivity, which is nothing else, at least the first approximation, than the turbulent diffusivity. So it equals the diffusivity of momentum in a turbulent boundary layer, which again, by classic scaling, will be just K von Karman constant times the friction velocity times the wall normal distance, Z. And here for everybody, I'm just taking Z as the vertical upward direction and X streamwise. Now, what about the still fluid terminal velocity? That's also an assumption. Or I guess, sorry, the vertical velocity is also assumed in this model to equal the still fluid terminal velocity. So essentially what Rouse and Prandtl assumed is that the vertical velocity of the particle in average everywhere in the system, regardless of the wall distance, it would be equal to tau pg, simply pointing downward in our convention. Under those conditions, then there is a very elegant solution of the concentration profile. So basically, the mean concentration simply follows a power law relation with the wall normal distance. It's basically decaying. The concentration is maximum. In fact, it's supposed to be infinite at the wall, and then it decays in a power law sense, following this Rouse number, which is something very similar, if you want, to the SV number. Is the settling velocity in still fluid tau pg divided by the, in this case, a velocity scale of the shear velocity. So to test this assumption, this model for inertial particles, we carried out extensive measurements in Minnesota, both in a large wind tunnel and in a smaller water open channel. The wind tunnel is a St. Anthony Falls laboratory, is a beast, is a 16-meter long, only the test section, with almost a 2 by 2 meter in cross section. And we reached velocities about 15 meters a second, which gave a Reynolds tau approaching 20,000 for the faster cases. And that is by far the highest Reynolds number for any particle-laden turbulence study in experiments. And then we used our beloved glass beads over a range of concentration. And these were in the interesting range in which particles are inertial but not ballistic. And we covered a broad range between 18 and 870 of Stokes plus, meaning that the Stokes number here is defined in the viscous unit, of course, as relevant for a boundary layer. And the Rouse number that I defined before is also in a range, but close to order 1. And then the water open channel flow, in fact, is a much smaller facility, but also an interesting one in which we use a paddle wheel such that there is no pump that will chew up our particles. And the particles are, in fact, these polystyrene 840 micron particles. The Reynolds tau is much smaller, but again, the Stokes number is in a regime in which we expect the particles to be inertial but not ballistic. Now, let's test our Rouse-Prandtl theory. As you remember, we have 3 main assumptions: the equilibrium of zero vertical flux, the Fickian diffusion, and the vertical velocity being equal to the still fluid terminal velocity. All right, so what about what we measure? What we measure in this situation is that the vertical flux is in fact very small, is less than 1% of the streamwise flux. So the first approximation, we conclude that for these 2 experiments that we run, we were in fact in equilibrium. And this is more of an assessment of the experimental setup as opposed to an assumption on the physics. This one, in fact, is key. The second assumption, we measure the turbulent diffusivity of the particles by tracking them Lagrangianly, and so we use a Taylor 1921 famous theory to basically deduce the diffusivity of the particles. And we see that the turbulent diffusivity of the particle really follows the behavior, the turbulent diffusivity of the momentum in the boundary layer very, very closely. So we do think that the second assumption also checks out. And then we have our third assumption, the fact that WP would be equal to tau PG. And we see that this is approximately verified only very far away from the wall, where we should expect it to be verified. Far away from the wall, we are in the outer region of the boundary layer. And so there, the particles are not living in a very turbulent environment, and they're not feeling significant shear. So they do fall with expected tau PG velocity. But as we approach the wall already for 100 wall units, essentially the vertical velocity becomes vanishingly small. And in fact, that shouldn't be too much surprising. If we take only the first two assumptions and we plug one into the other, what we deduce is that essentially the advective flux in the vertical direction should be just proportional to this term over here. So basically linearly proportional to the velocity, to the wall distance z. So at the wall, when z shrinks to 0, we do expect the vertical velocity to be equal to 0, even if the flux is not. And therefore, this kind of glaring hole in the Rouse-Prandtl theory shows up very clearly when we look at the results, because these dashed lines are exactly the Rouse-Prandtl theory prediction. Basically, these are shifted each one by a decade for clarity, but these show the predicted concentration for our particles for different Rouse numbers, and those are indicated here by different colors. And so, as you can see, there's the power law decay with respect to the wall normal distance. But if you compare our experimentally measured concentrations with the Rouse-Prandtl prediction, you see that maybe for the very small Rouse number, I should say, as we expect for non-inertial particles or weakly inertial particles, then the prediction of Rouse and Prandtl does hold. But the mismatch can become dramatic as you increase particle inertia. So in fact, for the fast falling particles, the misprediction of Rouse theory with respect to the concentration near the wall especially can be off by multiple orders of magnitude. All right, so with this, we believe we made some contribution on the study of small inertial particles in a very dilute concentration in turbulence. But of course, what about dense concentrations? What about non-spherical particles, which are so abundant in nature and in industry? And what about particles at interfaces? For example, particles floating on free surface, which are crucial, for example, to understand the spread of microplastics. Well, we are addressing these problems in separate projects that I won't have the time to talk about today. We are looking at the dense concentrations in vertical channels relevant to chemical reactors. We are looking at how small disks, which in fact look a lot like a plate crystal in frozen clouds, fall in quiescent and turbulent environment. And we are just building, in fact, we already have built some facility at ETH Zurich, and we are building new ones to study wind wave interaction and particle floating on breaking waves. So this is a facility I'm especially excited about in collaboration with the National Laboratory here in Switzerland. And that's because we believe that the problem of particle-laden turbulence is really a holistic one that we can only fully understand if we go beyond the narrow regimes in which I first have been focusing for a long time, without venturing into different regimes. And that's because the parameter space is really large. What we're looking at is an attempt that Luca Brandt and I made recently in a review paper of describing one possible shape of the parameter space. And I believe that at least 3 parameters are needed for you to place any particle-laden turbulence problem. The particle volume fraction, the particle density to fluid ratio, and the particle size with respect to the turbulent flow scale. And here I'm actually not explicitly looking at, for example, the Reynolds number of turbulence, and I'm not definitely looking at the particle shape. Whereas everything I talked about today is pretty much a point or at most a line in this system. And I have to say that the community, as far as I can tell, is mostly focused on one extreme or the other extreme, either large low density particles at high concentrations or small high density particles in dilute regimes. Whereas I do believe that there is a lot to learn by trying to bridge the gap of this parameter space and understanding exactly where the boundaries are, if there are, in fact, sharp boundaries in terms of particle turbulence behavior. So with that, let me quickly conclude. What I want to bring home as a take-home message is that inertial particles in turbulence, they very rarely fall at the same speed as they would do in still fluid. And today we saw two clear examples of that. Particles in homogeneous turbulence that fall 2 or 3 times faster than in still fluid, and a particle in a turbulent boundary layer that, at least close to the wall, they essentially don't even fall at all. As in they have a vanishingly small fall speed. And then another take-home message by comparing our data with field studies and trying to learn something from the comparison is that small spherical particles in turbulence can actually be used as a model for much more complex natural particles, such as snowflakes, for example. But we need definitely much more data, much more studies on this front, because we just started. Something that I think I can say after, at least I have very clear in my head after studying this type of problem for a while, is that gravity is very much important. There are very rare situations, only with a very intense acceleration of the flow, in which gravity doesn't play a significant role. So neglecting it, for example, in numerical simulations for convenience, which I understand, can sometimes really lead to conclusions that might be hard to extrapolate to an environment which is not zero gravity. And finally, I'd like to end up with this note from Leonardo. Leonardo was a great experimentalist, not only a great scientist in general. And he would say that first he will do some experiments before he proceeds, because my intention is to cite first experience and then reason to show why it is bound to behave that way. And that type of a kind of pioneeristic laboratory approach, experimentalist approach, is something I hold dear in my heart. I don't want to take too much of your time, so I'll just very quickly thanking the many collaborators that have contributed in various ways to the results I showed today in various institutions across the oceans, because most of what I showed you was actually carried out in my time in Minnesota. Many funding agencies were very generous to support me. I'm happy that we get recent support from the Swiss National Science Foundation, that in fact will provide the financial fund for a near sequence editor grant that my group just secured. And speaking of my group, these are the people that really need to be thanked, because they've done all the hard work. They come from the four corners of the world, and they've been amazingly hardworking over the years, especially during the pandemic. They've shown great resiliency and great ability for teamwork. Some of them, many of them have followed me from Minnesota, and many of them actually met each other only via Zoom for many months. And then they were already working together as a team, really in a display of a fantastic attitude and friendship. So with that, I'll thank you again, everybody, for the attention, and I'll be happy to take any question.
Thank you very much, Filippo. Thank you very much for your very nice and instructive talk. Very nice experimental results and the physical insights. And now the floor is open for questions, and I can perhaps start. Okay, Bala wants to start. Bala first.
Okay, Filippo, thanks for a great talk. I like you should be happy that John Eaton wasn't there. So your statement that old advisor, the word old, you should be glad that he didn't get to see it. Okay.
Past advisor.
Yes, past would be better. I have a question on a serious note. You made these measurements south of Minnesota, Minneapolis, where you say that the settling velocity for the inferred size based on Stokes number is much larger than the still fluid settling velocity. But there could be a big, large-scale downward motion in the region where you made measurements. So you only measured the particle velocity, but there could be in a region of downdraft, that even a light downdraft that could increase the settling velocity. The other what makes it more interesting is that the downdraft could be because of the increased concentration, because of the two-way coupling effect. So it's a very complicated problem. So it's very hard to conclude that the settling velocity itself is much larger in that region based on what you measured. At least that's what my initial thought was.
Right. No, I agree. It's a very complex problem. Every time you do field studies, you have to be very careful of what you conclude, because of course it's not a well-controlled laboratory experiment, of course. But in terms of the downdraft, or the possibility of having a significant downdraft, what we did was to, because we wanted to avoid such a bias, we carried out these measurements in the immediate vicinity of this Met Tower, where essentially we would track the three components of the air velocity over time windows that of course overlapped with the time window during which we carried out our imaging snowflake imaging experiments, and the vertical downdraft is negligible. In fact, in any atmospheric boundary layer very close to the ground, in this case, I mean, the measurements were only 10 meters from the ground, you can't really expect any significant vertical velocity in the mean. And of course, the mean is defined over a time scale, even just of a few seconds. Definitely over any time scale relevant for us to take our average for the vertical flow, for the full speed of the snowflakes. So I don't believe that the downdraft could be an explanation for what we're seeing. I do agree, however, that it's very possible that the particles would, in a sense, two-way couple with the snow. Excuse me, the snow would two-way couple with the flow, and they could, in fact, bring down air with them. But then I would say that that's not, in a sense, it doesn't stop me from concluding that this is caused by turbulence. Why? Because we do see these snowflakes also clustering, and that's something that, in fact, I'm very thankful, Bala, you asked me, because I can show one of my backup slides. Essentially, what we see here is that, let's see if I get to show my slides. What we see here is that if I look at my snow concentration, which we get from image processing, basically we can actually identify clusters of snowflakes in the images, and these are also clustered following the same power law as we find in the laboratory. And also, when we look at the falling speed of these clusters, we also see the same effect. So the clusters of snowflakes, essentially, they tend to fall at similar speed as any other snowflake, but then above a certain size, they kind of take off and they really fall much faster than other clusters. And finally, and this could be a hint that either preferential sweeping is happening or two-way coupling is happening, I cannot quite tell. You do see a clear correlation between the vertical velocity of the snowflakes and their concentration. In other words, for all these studies all these different campaigns that we looked at, regions of high concentration that have even the very dilute ones in which you might not really have a cluster, you do have the tendency for the particles to fall faster. So I do believe that the particles could be two-way coupled locally, and they could be dragging down fluid with them, and that could be a reason for the enhanced settling. But that to me is very much in line with a picture of particle-laden turbulence, except when you have enough concentration for two-way coupling. And I should mention that the snowflakes, at least in the densest cases that we looked at, the ones with most cluster, we estimated a volume fraction of about 10 to the minus 5, which would be something for which you expect two-way coupling if, of course, you base it on small spherical particles in homogeneous turbulence.
Thanks, Filippo. I think there is a question by Ted before others, and he wonders if electrostatics plays a role in these particle experiments and how you control it in your experiment.
Right. I don't think it does, because, of course, this always does in experiments if you don't control it. But one of the reasons why we moved away from polydispersed particles is because we wanted to have as little problem as possible with electrostatics. If you have a polydispersed system with very many particles, then you have a lot of electrostatics. We like to work mostly with the 50 micron and larger. The 30 microns, in fact, you could already have some electrostatic issues, but not at the concentration we looked at. Essentially, we use either screw feeders or we use the glass hour feeding systems, and we always verify that essentially in our images we wouldn't see any clump. So, and it's obvious to see a clump because these particles look like a finite number of pixels. So if you have 3 or 4 particles altogether, they will show up immediately as a spurious particle. So this is something that can be an issue if you don't pay attention to it, and that's something that I think is an underestimated issue that we really paid a lot of attention to.
Okay, thanks. I may ask one question, and the question is following. It is crucial that we, in order to derive conclusive conclusions, then maybe we should measure at the same time turbulence and particles, but possibly is not an easy task. And I was wondering if what is the minimum size at which of your particles that allow you also to measure turbulence in a way, so particles are big enough so that you can distinguish them from the tracers.
Right. Yes. So these are the two important factors: the size and intensity difference, I would say. So when you have particles that are substantially bigger than your tracer, of course, that's the key. But also if they are brighter as well, it helps. So then you can, what we do is typically to plot kind of on a scatter plot both the intensity and the size of all the objects we identify, and then you see clearly two groups of this, which I showed in the slide: dimmer and smaller versus bigger and brighter. And for us, at least in air where your traces are the 1 micron droplets, I think anything larger than 20 micron is pretty easy to tell. But the bigger issue is concentration. I would love to make those measurements of kind of the secondary structure function of the turbulence in, I don't know, 10 to the minus 3 volume fraction, but I don't think that's possible. We push it to 5, 10 to the minus 5, and that was already, I think, pushing it. Because of course we want to have we want to be confident on high order quantities like the structural function. Maybe if you're happy with the TKE alone, you can push 10 to the minus 4. I think that's the upper limit, because then the opacity of the system is very high, and of course then other things matter. How thick is your illumination sheet? Those are technicalities, but I think in general it's hard to push the concentration a lot larger than that for small particles, of course.
Thanks, Filippo. And Bala again.
I have one more question. Can I ask Alfredo?
Sure.
I want to go back to your interesting result that you showed on near wall resuspension of particles, where your profiles did not match with the Raussian profiles for large Rauss number, large particles.
Right.
And you sort of suggested that that is due to settling velocity. You didn't probably you didn't have time. Why? What's going on with the large particles? Their settling velocity decreases. If so, what could be the mechanism? Because you're anyway taking into account the turbulent dispersal that U prime, W prime separately. So I was just interested in your take on what could be the reason for this difference.
Right. I think if you want, mathematically it's easier to explain than physically. So let's see if I can share my screen again. So from a mathematical standpoint, or I guess this is simple algebra standpoint, once you accept that you are in equilibrium, then you essentially accept that you're going to have to balance your mean advective flux vertically, which is just the mean concentration times the mean vertical velocity, with an upward suspension. Now, if this upward suspension is driven by classic turbulence momentum transport, then the the fact that the turbulent diffusivity goes to 0 near the wall kind of answered the question, right? So essentially, there is nothing to counterbalance, but that's only if the flux is 0. Now, of course, then there are arguments that say, well, in fact, these two processes, the mean of action and the turbulent suspension, are in fact decoupled, at least instantaneously and mechanistically. So what is the mechanism or the reason for which your actual vertical velocity is limited? I think in that case, and we have measurements to support that, is the tendency for these particles to visit more ejections than sweep. So I don't have it here, unfortunately, I don't think. But there is, I'm looking at my backup slides, I don't think I have that one. There is a clear tendency for inertial particles in this range of Stokes and Rouse number to essentially visit more sweep, ejection in a quadrant analysis sense than sweeps. So the fact that they stay more in sweeps, in ejections, at least to my mind, is kind of the mechanistic explanation why their downward velocity isn't. It does become eventually close to 0. And then, of course, you could go on and say, okay, why do they visit that? But then it's a longer discussion.
Thank you, Filippo. There is a question by Charles. Please, Charles, unmute yourself and ask. Charles Petty.
And unmute. Okay, can you hear me?
Yeah,
I hear you.
I really enjoyed what you did today. That's really thought-provoking. So when you get a competition between the turbulence and the particles, especially in the troposphere, you mentioned that the gravity was on the table, but I never heard you put the Coriolis term on the table. And the Coriolis term is beyond the Kolmogorov scale, is the only thing there that can move stuff around. And it's anisotropic. It's not isotropic beyond the Kolmogorov scale. So I was wondering if you had a set of words that the role of the Coriolis terms in the physics.
Thank you, Charles. So, atmospheric effects at those scales, this is not something that I've looked at. And in fact, what I believe is that the scales at which, for example, Coriolis force acts on the troposphere, those are time scales and eventually length scales massively separated from what we're looking at here. So what we're looking at here is a particle which is either of size of Kolmogorov or smaller, right? So this particle will only be influenced by a range of eddies which cannot be too many orders of magnitude larger than itself. And so the fact that you at the planetary level or even in the atmospheric boundary layer level, you have a large scale motion driven by Coriolis, of course, is one of the reasons why then turbulence develops in the atmosphere the way it does. And then possibly the anisotropy that is caused by these large scale motions could run as deep as the Coriolis forces. These are the Kolmogorov scales. These I'm not sure. But here I'm just taking the stand that the energetic eddies in the atmospheric surface layer, which is 15, 20, 30 meters as far as I can measure, those are removed enough in terms of length scale and time scales from the large scale effects that I'm not going to regard them as significant. In fact, if I had to, I think if I had to match the Rossby number for at that scale, in the laboratory, I think the things that I will have to use a rotating platform that rotates, too small to make any difference, or too slowly to make any difference.
So back in, can I make another comment?
Sure.
So back in the 1950s, Batchelor wrote a really nice book on homogeneous turbulence. And in chapter 5, he looked at isotropic turbulence in the wind, I don't know if it was a wind tunnel or a water tunnel or what, I just forgot that aspect. But when he got away from the screen that put the particles in, they were isotropic just behind the screen. And when they continued to flow, and it was one of the largest pieces of equipment of its time, so it had time to do something else. And what happened in that, and you go to chapter 5, you'll see it yourself. The particulates, the energy of the particulates are the scales below the Kolmogorov scales went anisotropic. And he, in Batchelor, in his book, he said, we don't understand this. So my question, Professor Coletti, does anybody understand the Batchelor observation from the 1950s? Every time I ask my friend John Foss, he says it was just a bad experiment. What, do you have an opinion of that?
I don't want to, contradict John Foss, far from me. I don't know if it was a bad experiment though, but we did actually do measurements in our chamber, looking at the level of anisotropy, because our chamber is anisotropic because it has 2 arrays of jets firing at each other, right? It doesn't have 8, so there is a broken symmetry there. And so we know it's a large scale anisotropic, and so the RMS velocity fluctuations are higher in the horizontal direction than in the vertical direction or the spanwise direction. And that's very much the same as in the atmosphere, I would say. And then we looked carefully at the level of isotropy and how this changes as you change the scales. Because of course, you expect a return to isotropy from Kolmogorov onward. But in fact, we didn't quite see a clear return to isotropy for the high order quantities. But I have to say, these are things for which you need extremely high resolution, which I think we had, but high accuracy, all of this. I think it becomes a question for probably direct numerical simulations or dedicated experiments in which you're really focusing on the small scales. To a point, I even wonder if it matters, because at the end, for example, in at least for certain problems like in natural environment with particles falling down with gravity, that breaks the isotropy, the symmetry so openly immediately that I don't know that Kolmogorov scales being fully isotropic would change a lot.
Okay, thank you for the response.
Oh, thanks.
Thank you very much. Maybe there are other questions? Or maybe not. I think we already fired a number of questions to Filippo, and I think that I think this seminar was an excellent seminar from your side, Filippo, and this is also testified by the large audience. We just topped at well, we almost topped at 100, because I think it was summing the YouTube attendees and the Zoom attendees. We are about 100. So thank you very much again. I thank